Yes, it's good, sir.
It's okay. Now, so yesterday we looked at how to find inverse using the Euclidean algorithm. And I said that we can get inverse also using Fermat and using the other method we'll be looking at is the Euler theorem. And why I'm showing these methods, all of them, is that sometimes you may want to combine them to make your work easier. And like the Fermat is what is stated here. For the Fermat, we saw yesterday that no, we didn't look at Fermat yesterday. No, I think we looked at it. Yeah, what we didn't see yesterday was how to get the inverse using Fermat. But the Fermat theorem, we stated the Fermat theorem and said that the P here should be prime and should be a number that cannot divide the A here. So we saw that the GCD of A and P must be 1 for you to use the Fermat's little theorem. But we shall look at another theorem that does not restrict that this number should be prime. Now, so if you have a very big number and the power is too huge, for instance, let me talk of this 2018, can even be bigger than this, mod, let me say another number here. So the important thing is for you to find out whether this number is prime. Once you find out whether this number here is prime, then you know that you can use the Fermat's little theorem. And finding whether this number is prime, there are so many ways you can use the algorithm to find out whether this number M here is prime. And so once it's prime, then you know that you will use the Fermat's little theorem. You just subtract 1 from it, and raising it to A, it should be equivalent to 1 mod P. Now, so today, therefore, we're supposed to look at how to find inverse using the Fermat's little theorem. So that is what I'm supposed to share. Yes, so this is where I'll start from. Now, the statement, I begin by the statement here. And the corollary here says, if P is a prime number, and if P cannot divide A, if P is prime and cannot divide A, then you can find the inverse of A. You can find the inverse of A, and the inverse of A will be given by A raised to P minus 2 mod M or mod P. So P must be prime. So if P is a prime number which cannot divide A, then the inverse of A will be given by A raised to P minus 2 mod P. So you just reduce that to mod P. So let's look at the example here. The example that I have is find the inverse of 7. Now we know we can use Euclidean algorithm, but I want us to use the Fermat's little theorem. So by Fermat's little theorem, 23 here is prime. 23 cannot divide 7. So Fermat's little theorem can be used. And what it then says is that the inverse of 7 will be given by 7 raised to P minus 2. P is 23, minus 2, that gives us 21. Mod 23. Now, so this is the inverse of 7. So what we then do is you can use the first powering algorithm to find out what 7 raised to 21 is. So you just do it, 7 raised to 1 would be 7. 7 raised to 2 would be 49. But now, if 23 were to go into 49, what would be the remainder? 23 goes there twice. 23 goes there twice, and the remainder is 3. Because, yeah, that would be 46 from that. The remainder will be 3. And then we are using the first powering algorithm. We want to go up to 7 raised to 21. So then what is 7 raised to 4? 7 raised to 4 would be 7 squared. You square 7 squared. You square the one above it. So I square this, I get 9. What about 7 raised to 8? 7 raised to 8, I square this, would be 81. 81 mod 23. So how many times does 23 go into 81? Let me see, 23, what is 23 times 3? That would be 69. Let me subtract and see what I get. It will be 12. It will be 12. So 7 raised to 8 is 12. What about 7 raised to 16? 7 raised to 16. So that means I square again the one above, and that gives me 144. So how many times does 23 go into 144? I just now, let me use my calculator. So I have 144 divided by 23. It goes there 6.2 times. So what is the remainder? So the remainder will be 6. The remainder will be 6. Now, so what we needed was 7 raised to 21. So how do we get 7 raised to 21 from what we have? It will be 7 raised to 16. 16 plus what? Because we want 21 to be the power. I'm left with the 5 to make it 21. But I don't have power of 5. What I have is power of 4. And then power of 1. So this is same as 7 raised to 16 plus 4 plus 1, which is 21. And so, using the law of indices, this would be 7 raised to 16 times 7 raised to 4 times 7 raised to 1. But 7 raised to 16 is 6. 7 raised to 4 is 9. And 7 raised to 1 is 7. We multiply this and divide it by 23, then write the remainder. Let me just multiply. This will be 6 times 9 times 7. I'm getting 378. 378 divided by 23. It goes there 16 times. What will be the remainder? The remainder will be 10. The remainder will be 10. So this 10, therefore, is the inverse of 7. Is the inverse of 7. So we used the Fermat's little theorem to do this inverse. And as I said, sometimes you need to combine the methods. You can see we began by Fermat's little theorem. And then towards the end, we've used the fast powering algorithm. We look at another example. Now the working is here. The working is here, the typed one. So the next example is here, says, find the inverse of 12 mod 19. So I need, supposing 19 was a very huge number, I would only require to use an algorithm to find out whether it's prime or not. If it's prime, I can proceed and use the Fermat's little theorem. So the only thing I need is just to find out whether it's prime. Now, so if it's prime, then what is the inverse of 12 by Fermat's little theorem? The inverse would be 12 raised to p minus 2. That is 19 minus 2, which is 17 mod 19. Then I use fast powering algorithm to work out this. So 12 raised to 1 would be 12. 12 square would be 11. 12 raised to 4 would be 7. 12 raised to 8 would be 11. 12 raised to 16 is 7. So if I square it again, it will be 12 raised to 32, which is beyond 17. So I stop at this point. Now, so how do I get 17? 17 will be 16 plus 1. Those are the only powers I have. Those are the powers 1 and the power 16. So 12 raised to 17, therefore, is written like that. From here, you use the laws of indices. So that would be 12 times 12 raised to 16 times 12 raised to 1. But 12 raised to 16 is 7. 12 raised to 1 is 12. So when you multiply this, you get 84. Get 84. Then 19 into 84, the remainder will be 8. So 8 therefore becomes the inverse. It becomes the inverse of 12. 8 is the inverse of 12. That is how we use the Fermat's little theorem to find inverses. Now, I decided also to use to give you a huge number and then leave this as exercise for you, a huge number. So this number, I don't know whether it's prime, but it's you first of all to find out whether it's prime. You find out whether this one is prime. And if it's prime, then you can employ the Fermat's little theorem. But the answer I've given you that the answer will be 1284, 1284. So it's just you to go through the working and confirm that is the correct answer. Now, the other use of the Fermat's little theorem is to test whether a number is prime. That's what I want to show you, how to test if a number is prime using the Fermat's little theorem. Now, there are so many ways, there are so many algorithms for testing whether a number is prime, but I just want to show you how to test using the Fermat's way first. Now, what does Fermat's theorem say? It says that if a number is prime, if P is prime, and if P cannot divide A, then A raised to P minus 1 would be congruent to 1 mod P. So this is how we test. This is how we test if a number is prime. So what that means, if I'm given this number and I'm asked to test if it's prime, I only need to pick another number less than it. I pick another number less than 19, and that let me say I pick 7. Let me take A to B, even 8, any number less than 19. Then take this A, raise to it P minus 1, and do it mod P. See what you get. So I just repeat that. What I said is, I'm given a number, I don't know whether it's prime. And the question is, can I find out whether it's prime? So supposing I'm given a very huge number. Let me say I'm given this number. And I don't know whether it's prime. And I want to test whether it's prime. I'll pick another smaller number. Let me say I pick 2. So that 2 raised to it this number minus 1. So this number minus 1 would be 10, 9, 9, 8, 2. Then reduce this mod 10, 9, 9, 8, 3. So at this point, you'll be using the first powering algorithm. Just use the first powering algorithm. If you find that it's equivalent to 1 after doing that, then it means the number is likely to be prime. It doesn't mean it's prime. It's likely to be prime. But if you find that it's not equal to 1, then you are sure that this number is not prime. So there are two issues here. If you find that it's equal to 1, It means the number is likely to be prime. It doesn't mean it's prime. It means it's likely to be prime. But once you find that it's not equivalent to 1, then you are sure the number is not prime. So what happens therefore, I've tested 2. I would also pick another number and test. I'll pick 3 and test. I'll pick 4 and test. Pick as many as possible and test. Now, let me say, for instance, I picked 4 and tested. And after testing, I found that it was equivalent to 1. Then picked 3 and test. And 3 tells me that it's not equivalent to 1. Then 3 has told me the correct thing. Because this one, after getting that it's equivalent to 1, the information I got from this first test was that the number is likely. It's not an assurance that it will be prime. It's not an assurance. Just telling me the number is likely to be prime. But once I test another number, and then the other number contradicts, then that second test is correct. So this other first number that I tested becomes a liar. We call it a liar. So this is the Fermat's liar. It lied to me that the number was prime, but then when I tested another one, the other one gave me a contradictory message. So this one is now a confirmation that the number is prime. So that is what we do using the Fermat's little theorem to test if a number is prime. That is what I've written here. I've said to test if P is prime, you would pick a random integer A, not divisible by P. Then test this if it holds. Now, if it fails to hold, I've said if it fails, for the number you picked, if you picked A to be 4 or 3, if it fails to hold, then it means the number is not prime. It's therefore composite. So the random number A chosen should be between, just is any number which is smaller than P, any smaller number smaller than P. Now, I've said that it's always unlikely. It's unlikely that a number chosen would say that this is equivalent to 1 if indeed P is not prime. It's very unlikely. It's very unlikely that it will say that this test would say that A is equivalent to A raised to this power is equivalent to 1 if P is not prime. It's very unlikely. But there are cases where that happens, and there are very few cases. So I've said, that is what I've said here. I've said that if any random number A holds this, when P is composite, then we call such A Fermat liar. In this case, N will be called pseudo-prime. Is the number that you are testing, whether it's prime or composite, will then be called a pseudo-prime to base N. And in this case, we would pick another number and test. We would pick another number and test. And if that other number gives us a contradictory statement, then that new number is then called a Fermat witness. Is that Fermat witness for compositeness. So it has said that this number is indeed composite, but the other one had lied to us. But what I've said that to get such instances where we have a number lying to us, those cases are very minimal, but they happen. That is why I said, if you get this, it only says that P could be is likely to be prime, but it's not a sure test that it's a prime number. So for you to be sure that it's a prime number, you have to test all the numbers less than P. All the numbers less than P. Now, let me show you an example. I want to test whether 7 is prime. So I pick a small number and I want to test whether it's prime. Now, for me to be sure that 7 is prime, I'll test all the small numbers less than 7. All the small numbers, so I test 2 raised to p minus 1. And I want to see what I get. When I did that, I got 1 mod 7. Then I decided to test 3. And 3 gave me 1 also. Then I test 4. 4 gave me 1. Then I test 5. 5 gave me 1. Then I test 6. 6 gave me 1. So I've tested all the numbers less than 7. All the positive numbers less than 7. So this then confirms that 7 is a prime number. This confirms. But if I would have just picked 1 and tested, that will not be a sure test. That will just say that 7 is likely to be prime. But since I've tested all the smaller numbers, then we can be sure that 7 is a prime number. Now, let me look at another example again. I want to test whether 221 is prime. So I pick any smaller number between less than any smaller number smaller than 221. I've decided to pick on 38. So I perform 38 raised to p minus 1. P minus 1 is 220. So I want to find 38 raised to 220 mod 20 or 221. Now, when I did that, I found that 38 raised to 220, when you use the first powering algorithm, it will give you 1 mod 221. So this does not confirm that 221 is prime. It only tells me that 221 is likely to be prime. Because I've only tested 1 number, so I cannot for sure say that it's a prime. This one is a prime number. I've only tested 38. So then I decided to test again another number. I decided to test 24. So I take 24 raised to 220. So 24 raised to 220, I found it to be 81. So this is not equal to 1. So that means I'll now use this test. This test must be true. It's telling me that 221 is not a prime number. That's what it's telling me. So I'm now able to, I can say for sure that this number is not a prime number because this test has rejected. So therefore, then the first number 38 had lied to us, so we call it the Fermat lie. It was saying that 221 is prime. So 24 is then what we call the witness. 24 is the witness. So it has witnessed that it's a witness that this number is composite and not prime. It's not a prime number. So what that means is that at the end of the day, we are able to tell that a number is prime or not. Whatever the result we get, we're able to tell that the number given to us is prime or not using the Fermat's test. Because what we are saying is, at the end of the day, I've been given 221. I tried 38, and 38 lies to me. It tells me that the number is likely to be prime. I pick another number and try it again, and it tells me that 221 is not prime. So at the end of the day, I know that this number is not prime. Now, as I said, we have other algorithms one can use to tell if a number is prime or not. But I decided to first of all look at this Fermat test. Now, this exercise, I think I had already sent this exercise. Show that the following algorithm will compute the value of this. So those are numbers raised to a bigger, if a number is raised to a bigger value, and we are using the successive squaring. So maybe look at it. The continuation, this is just a continuation of that exercise. Now, this continuation, I like this part G. Part G says, compute this number by successive squaring and use your answer to say whether this number is prime or not. Do it by successive squaring. So that means if you find your answer to be 1, then you can say that this number is prime. But if you find that the answer is not 1, then you can say that this number is not prime. It's composite. So that is what this question wants us to do. Now, I want us to look at the Euler theorem, and we shall again be using it to find the inverse later. What does the Euler theorem say? Slightly different from what the Fermat's theorem says. The Euler theorem, we are given a number. This number is any integer. Any integer. It doesn't need to be prime. But the Fermat's had put a condition on this number. This number in the Fermat's theorem was to be prime, must be prime. But for this Euler theorem, it's any integer. But the only condition here is that this integer here and this integer must be relatively prime. A and M must be relatively prime. That is the only condition that Euler gives us. Yes. So that means the GCD should be 1. Is that okay? Can you still hear me? Can you hear me?
Yes, sir, we can hear you very well.
It's okay, thank you. Now, so that is the only condition of the Fermat's, the Euler theorem gives us, that this number M should be relatively prime to A. And we say what that means is that two numbers are relatively prime if their only common factor is 1, or if their GCD is 1. Now, the question here is find the last digit. Find the last digit. If I'm given 27 raised to 71, what would be the last digit? I know this will be a very long number. This will be a very long number, but I'm only interested in the last digit. What is the last digit here? So that is the question, and that's the question I want to answer. The place value of the last digit would be tens. That's the place value. If we can, is it tens or ones? Or how do we do those place values? Supposing I'm given, okay. Suppose I'm given this number, 7, 8, 3, 4. The number I'm interested in is this. This is the number I'm interested in. So it's only one number. It's only one number. So what I do, for me to get that one number, I would reduce this, what I'm given here, mod 10. I'll reduce it mod 10. But if I would have been asked to find the last two digits if it's the last 2 digits, then I would reduce it mod 100. That's what I was talking about, the place values. Now, so if I'm asked about the last 3 digits, then I reduce it mod 1,000. The last 3 digits, I reduce it mod 1,000, and so on. So let's do this one. The question is, find the last digit. So for me to find the last digit, I take 27 raised to 71, reduce it mod 10. Now, I want to use, because I'm talking about the Euler theorem, I want to use the Euler theorem. Otherwise, I would have used the first powering algorithm and found the answer. And again, in some cases, we will have to combine the two. So using the Euler theorem, I want just to reduce this number using the Euler theorem. Euler theorem tells me that this number here, for me to use it, this number and this one must be relatively prime. And that is something I'm saying, they're relatively prime. So the first thing I would do, since 27 is larger than 10, I will reduce this number first. 27, reduce it first. So 27 is the same as 7 mod 10. So 10 goes there, and then the remainder is 7. So that means, therefore, if somebody gives me 27 raised to 71, this is the same as 7 raised to 71 mod 10. So these two are the same. These two are the same. Now, so then, since I've reduced it to 7 raised to 71, that's what I want to reduce. That's what I want to solve out. Raised to 71 mod 10. What does Euler theorem tell me? Euler theorem tells me, Euler's theorem says that 7 raised to 5 of 10 would be the same as 1. Yesterday, we looked at how to find the phi of a number. We say that if P is prime, then phi of P will be P minus 1. That's what we said. Then we said that if P is not prime, phi of n, where n is not prime, will be given by 1 minus 1 out of P1 multiplied by 1 minus 1 out of P2, and so on, up to 1 minus 1 out of Pk, and then times n, where the P1, P2, all the way up to Pk are the prime factors of n. That's what we said yesterday. So this 10 here is not prime. And therefore, what is phi of 10? The prime factors of 10 are 2 and 5. These are prime factors of 10. In fact, you can just do that by factorizing 10 into its prime factors. 2 will go there 5 times, and 5 will go there once. So 10 is just 2 times 5. And so these are the prime factors. So what is phi of 10? Phi of 10 is 1 minus a half multiplied by 1 minus a fifth, then multiplied by 10. 1 minus a half is just a half. 1 minus a fifth is 4 out of 5. Then times 10, and you get 4. You get 4. So back to my question here. 7 raised to 5 of 10 is the same as 7 raised to 4. Is equivalent to 1 mod 10. But what we're supposed to get is 7 raised to 71. What we have is 7 raised to 4. So we write 71 in terms of 4. And when you write 71 in terms of 4, what do you get? By division algorithm. By division algorithm, 71 is the same as 4 times 17, and the remainder will be 3. Yesterday, we noted that when you write, we noted that after writing into as using division algorithm, after writing that, it means 7 raised to 71 is the same as 7 raised to this remainder, which is 3 mod 10. That's what we discovered yesterday, because this other one will give us 1. 4 raised to 7, 4 times 17 will give us 1. Just give us 1. What I mean is this: 7 raised to 4, then raised to 17 will give us 1, because 7 raised to 4, we know it's 1. From this, we know it's 1. So this is just the same as 1 raised to 17, which is 1. That is why I leave it out. I only concentrate on the remainder. So 7 raised to 71 is the same as 7 raised to 3 mod 10. What is 7 raised to 3? This is a small number. You can do it using a calculator. 7 raised to 3. That's what I want to do. 7 raised to 3, what is it? I'm getting 343. Mod 10, which is 3. In fact, the question wanted the last number, and the last number I can see it is 3. So, but I had to just go forth and find it here. It's still 3. Whether I divided 10 into that and get the remainder, the last number is 3. So what that means is that if you were to multiply this number, 27, 71 times, you will find that the last digit will be 3. That's what it means. And you can see the method we've used. So you multiply 71 times and the last digit will be 3. Let me just take a small example so that you can see it works. I want the last number of 5 raised to, let me say, 6. Of course, when we use a calculator, we know what that answer is. 5 raised to 6. What is it? 5 raised to 6. My calculator says this number. If I use my calculator, it says this number is supposed to be 15,625. But I'm only interested in the last digits. That's what I'm interested in. So I want to do it and find the last digit. I will do this question mod 10. I'll do mod 10. I want to use the Euler theorem. Euler theorem says 5 raised to 5 of 10 is supposed to be 1 mod 10. We've already seen that 5 of 10 is 4. That means 5 raised to 4 is 1 mod 10. But what I want is not 5 raised to 4. I want 5 raised to 6. I want 5 raised to 6. So at this point, we are using the division algorithm. Division algorithm. And we want to write 6 in terms of 4. This is the same as 4 times 1. And the remainder is 2. So what I was then saying is that if I'm given 5 raised to 6, I would say this is the same as 5 raised to 2. This is a remainder here. This is a remainder. So I ignore this other part, because 5 raised to this part would give me 1. So I take 5 raised to this, then mod 10. This is 25 mod 10. And so it tells me the last digit will be 5. It tells me the last digit will be 5. So I've used a smaller method, a smaller example so that we can see it works. So that means that if I multiply 5 6 times and write that number that I get, the last digit of those numbers will be 5. So let's look at another example. So I've done 2 examples that we are looking for the last digits. I'll not do example 60 because we are just reducing it mod 10. No, but I think I should do it. I think I should do this example 60. Slightly different because the number that I'm given 55 is not relatively prime to 10. And so I had to work around it. I've been given 55 raised to 29. I want to reduce it mod 10. And I wanted to do this using the Euler theorem. But as I said, there are several methods you can do this. You can do it using, I know you cannot do it using the Fermat because this number is not prime. This number is not prime, so you cannot use Fermat. If it were prime, you would still use Fermat, will still work. But since it's not prime, I think the other method that can work is the fast powering algorithm. The fast powering algorithm. But I want to use this. I want to use Euler phi. So to use Euler phi, the first thing I will do, I would say this 55 can be decomposed into as a product of a prime number and non-prime number. So that means if somebody gives me 55 raised to 29 is the same thing as 5 raised to 29 times 11 raised to 29. So at least I have somewhere I can use the Euler phi. So this means I will work out this one. I will work out 5 raised to 29 mod 10, get the answer, then work out 11 raised to 29 mod 10, get another answer, then multiply the 2 answers. So I had to force until there's somewhere I can use the Euler theorem. So from there, I think we can always do it. So the first, let me do the 5 raised to 9, no, 11 raised to 9 first. Let me do 11 raised to 29. So 11 raised to 29 first, mod 10. 11, 10 are relatively prime. And so that means 11 raised to 4 by Euler theorem should be the same as 1 mod 10. Should be the same as that. So then, what about 29 in terms of 4? By division algorithm, 29 in terms of 4 would be the same as 4 times 7, and the remainder would be 1. So that means 11 raised to 29, therefore, is just the same as 11 raised to that remainder, which is 1 mod 10. And so the answer is just 11. Mod 10, of course, mod 10. Mod 10. This is 1. Mod 10, this is 1. Mod 10, 11 mod 10 is 1. Now let's now come back and do 5 raised to 29. 5 raised to 29, since it's not relatively, 5 is not relatively prime to 10, I would use that part, I will use the fast powering algorithm. I will use this fast powering algorithm. So 5 raised to 1 would be 5, 5 raised to 2 would be 25, which 25 divided by 10, the remainder would be 5. 5 raised to 4 would be 5, 5 raised to 8 would be 5, all are long up to 5 raised to 16, which is also 5. So 5 raised to 29, therefore, is 5 raised to 16 plus 8 plus 4 plus 1. And so this part is 5, this other part is 5, this other part is 5, and the other part is 5. 5 squared, we say it is 5. So that means these two 5s will give us 5. These two 5 also will give us 5. 5 times 5 will also be 5. Now, so the remainder, when you multiply, and no, the remainder when you take 5 raised to 29 mod 10 is 5. And the other remainder was 1. So multiplying those two gives you 5. So what we wanted was the last digit. It is there 5. 5 times that 1. And that's what I did here. So the last digit therefore is 5. Now what about the 2 digits, last 2 digits? We said we would do that mod 100. We'll do that mod 100. So we've been given a question here. And the question is, what are the last 2 digits here? So I'll do this mod 100. Now, this number is relatively prime to 100. Use the Euler theorem straight away. The first thing you do is to realize that this number is bigger than 100 and reduce it mod 100. So if 100 were to go here, the remainder will be 11. So that means somebody giving you this number and raising it to 71,023 is just the same thing as somebody giving you this. Then raising it to that power, mod 100. Now, so 11 is still relatively prime to 100, so you can use the Euler theorem, which says that 11 raised to 5 of 100 will be 1. And I know you now understand what it means by mod. Mod, we are only writing the remainder here. That if 100 were to go into this number, the remainder will be 1. So we only need now to get what is 5 over 100. 5 over 100 is the same as a half times 4 out of 5 times 100, which is 40. You know where I got 4 out of 5 and where I got a half from. Let me just remind you that the factors in 100, what are the factors in 100? So I just decompose this number. This would be 50, decompose again 25, and then 5 there would be 5, and 5 here would be 1. So I've seen that 100 can be written as 2 raised to 4, or 2 raised to 2 times 5 raised to 2. What is important are the factors, prime factors. The prime factors in 100 are 2 and 5. That is what is important. And so that 5 over 100, therefore, 1 minus 1 out of the first factor, prime factor, times 1 minus 1 out of the second factor, then times 100. This first bracket here gives you a half, and the second bracket there gives you 4 out of 5. When you multiply that by 100, what you get is 40. What you get there is 40. So the phi, Euler phi of 100 is 40. So that is where we had reached. So let me now continue from there by just erasing this part a bit. So the Euler phi of 100 is 40. We are there. So that means we continue from here. We then know that 11 raised to 40 would give us 1 mod 100. But what we are given is 11 raised to this number. So division algorithm says what? Division algorithm, I write this number using a division algorithm. So the number 71, 023 will be the same as 40. 40 goes there, 1,775 times. 1,700, and the remainder is 23. The remainder is what is very important from the way we began the class. You've seen how the remainder there is very important. And what the importance is, we just then say that 11 raised to 71, 023 is the same as 11 raised to this remainder, mod 100. That's how the remainder becomes very important. Once you get the remainder, your work becomes very easy. Now, at this point, you can now use the first powering algorithm. At this point, if this number is not prime, if it will be prime, you will have used the Fermat theorem, but it's not prime. So there are other methods you can use the first powering algorithm. 11 raised to 1 is 11. 11 raised to 2, just square 11. When you square 11 and divide by 100, the remainder is 21. 11 raised to 4, just square this part. 21 is square, then divided by 100, the remainder will be 41. And then 11 raised to 8, you want to go up to 11 raised to 23. 11 raised to 8, you square this 41, divide by 100, the remainder will be 81. 11 raised to 16, again, to get 16, we've squared 8. We've squared this. We've squared this. Well, it's when you square this, you get 11 raised to 16. So we also square this. And when you square this 81 and divide by 100, the remainder of the 61. Now, if you square again, you would get 11 raised to 32, which is beyond what we want. What we want is 11 raised to 23. So that means we then use the ones we have. We cannot square again. So what is 11 raised to 23? It will be the same as 11 raised to 16 times 11 raised to 4 times 11 raised to 2 times 11 raised to 1, because 16 plus 4 plus 2 plus 1 is what gives us 23. That's why we're multiplying those ones. Yes, because 16 plus 4 will be 20. 20 plus 2 will be 22. And then plus 1 will be 23. Now, so what is 11 raised to 16? That is 61. 11 raised to 4 was 41. 11 raised to 2 was 21. You can see it here. It's 21. 11 raised to 1 is 1. Then when you multiply the whole of this, what you get is this number. Dividing by 100, or even without dividing by 100, you can see the last 2 digits. You can see the last 2 digits are here, which are 31. Now, the way we did this the other time, we discovered that in some cases, you may want to multiply this number and find that your calculator cannot do that. So what you then do This 61 is very close to 100. You can reduce it more than 100. You can say this is negative 39. Negative 39. But this is a small number, you can just multiply. And this is another smaller number. So you can do that. That is one way. The other way, you can multiply 2's, as I did in another example earlier. Formula this 2. Well, let's see what you get. 61. Let me just use my calculator also. 61 times 41. I'm getting 2,501. But I'm doing it more than 100. What I got when I multiply was this. I got this. So when you do more than 100, you find that these two numbers, when you multiply them, they give you 1. Then now multiply by 21. Again, that one gives you 21. Then multiply by 11. So what is 21 times 11? 21 times 11, that is 231. 231. I'm interested in the last digit, 2 digits, which is like 31. The last 2 digits is what the question wanted. So if you find that these numbers could be bigger than what your calculator can accommodate, just do bits. Multiply first 2, then the answer you get multiplied by the next number, the answer that you get multiplied by this next number. As you reduce, you do it as you reduce more than 100. Now, so we've seen how to find the last 2 numbers. If the question was find the last 3 numbers, you would do it more than 1,000. And the example is here. We are doing it more than 1,000. Find the last 3 digits. Find the last 3 digits. So that means you do it more than 1,000. And this 17 again, you can see it's relatively prime to 1,000. That means the Euler theorem can be applied. So what the Euler theorem says is 17 raised to 5 over 1,000 will be congruent to 1. More than 1,000. The prime factors of 1,000 are still 2 and 5. So that means 1/2 times 4 over 5 times 1,000 gives you the 5 of 1,000. 5 over 1,000, which is 400. Just to remind you again what phi means, phi of n. I just remind you again what it means. We said phi of n are the smaller numbers less than 400, less than n, and relatively prime to n. Smaller numbers which are less than n and are relatively prime to n. So you're saying that from 1 to 1,000, from 1 to 1,000, we have 400 numbers which are relatively prime to 1,000. From 1 to 1,000, we have 4,000 numbers, no, 400 numbers, which are relatively prime. And that's what we did yesterday. And those numbers are just 1. 1 is relatively prime to 1,000. 3 is another one. 4 is not. 5 is not. 6 is not. 7 is another one. Those are numbers which cannot divide 1,000. There is no other common factor between them and 1,000. 8 is not. 9 is. So there are so many of them. There are 400 of them. There are 400 of them. So that was just a reminder of what we mean by 5 over 1,000. Also, we did that yesterday, but it means numbers smaller than 1,000, which are relatively prime to 1,000. Okay, so let's continue therefore. We have found what phi of 1,000 is. So now we can do our question there. So 17 raised to 5,000 is the same as 17 raised to 400. No, 400. And this is the same as 1 mod 1,000. But what we want is not 400. What we want is this number. The power. The power that we want is this number. So what is this number in terms of 400? The number 2,000, what number is this? 20,000. 20,000 and 1. In terms of 400, is the same as 400 goes there 50 times. And the remainder is 1. So as we've already said, somebody giving you 17 raised to that number is the same as 17 raised to the remainder. The remainder here, which is 1. Mod 1,000, which is at 17. The question was find the last 3 digits. Doing this has given us the last 2. So it means the other one is just 0. So that the last 3 digits are this. So that means if I was to multiply this 17, this number of times, I would find that it has 3 last digits, and those 3 last digits are these ones. These will be the last 3 digits. I'm not concerned with the other digits. I'm only concerned with the last 3. Okay, so let's move to something else before we end. This one you'll do it. Oh no, you've not done the remainder. Let's just take. But it's just the same thing. It's just the same thing. Doing the remainder and find the last 3 digits, just the same thing. But now this one, we are doing the remainder on division by 23. The other one, when you find the last digits, if it's the last 3 digits, you're doing it on division by 1,000. That's why you're doing it mod 1,000. If you're finding the last 2 digits, it's the same as finding the remainder on division by 100. If you're asked to find the last 2 digits. That equation is the same as find the remainder on division by 100. If it's find the last digit, that equation is the same as find the remainder on division by 10. So the way we approach those questions is just the same. Find the remainder on division by 23. So if you have an algorithm, you check if this number is prime. If I'm saying if the number is too huge, if it's too huge, but for this one is a smaller number, I can see it's a prime. And so being a prime number, then I know that there's no common factor between it and this one. There's no common factor. Because if I take this 23 divided into this, I don't get any other number. So there's no common factor. So those 2 numbers are relatively prime. So since they are relatively prime, I know that the Euler theorem can be used. What does it say? It says that 524 raised to 5 of 23 would be equivalent to 1 mod 23. But you can also reduce this number. You can also reduce 523. It's a huge number. 524, you can reduce it. Or you can work with it the way it is. There's no problem. You can work with it the way it is. I can see in my working here, I reduced it. But let me now work with it so that you can see that we can also work with it. Not always that you must reduce it. The only thing I'm supposed to get is 523. 23 is a prime number. We said that if it's a prime number, we just subtract 1 from it, and that gives us 22. That means what I need, what I have, therefore, is 524 raised to 22 is the same as 1 mod 23. But the power that I want is 999. The power that I want is 999 4 times. In terms of this 22, it will be the same as 22 will go there 454 times, and the remainder will be 11. So therefore, 524 raised to that 994 times is the same as 524 raised to the remainder 11 mod 23. At this point, I would use the first powering algorithm and find 524 raised to 1, which is just 524. Then 524 raised to 2, I squared what I have above. Let me just use my calculator. And then remember, it's mod 23. So 524 times 5 times 524, it's giving me 274,000, and then 576. Let me divide that by 23. It goes there 11,938 times. 11,938 times. What will be the remainder? Just a minute. Let me use my calculator. So let me again divide by 23. My calculator is not responding. Now, anybody who is using a calculator so that you can move from there. Mine is not it's not responding the way I want it to respond. And I don't have a piece of paper to write what I have here. Okay, let me look for another calculator. But I hope you also have a calculator so that we can also move together. Okay, so let me again do it. 524 times 524, then divide by 23. No, this calculator is not working. Five 24 times 524. Okay, let me change. Okay, so 524 times 524 is that, then divided by 23. Yeah, this is now okay. It's going there how many times? 11,938. 11,938. 11,938. So the remainder will be 2. The remainder will be 2. I hope I did the correct thing. Let me just do it again. 524 times 524. Yes, that's what I get. Then divided by 23. And then it goes there 11,938 times. 11,938 times 938. The remainder is 2. Okay, so now I get 524 raised to 4 will be this 2 square, which is 4, And then 524 raised to 8. How many times do I want to do it? I want to do it 11 times. So if I raise to 8, it will be 16. This is 4 square, which is 16. Then 5 raised to, I think that is the last one. That's the last one, yeah, because I'm going to 11. So what that means, therefore, 524 raised to 11 is the same as 524 raised to 8 plus 2, then plus 1, which is 524 raised to 8 times 524 raised to 2, 524 raised to 1. But 524 raised to 8, we found the answer to be 16. Then this other one, found the answer to be 2. Then this other one, the answer is 524. The answer is 524. So just multiply this one, mod 23. So what is that? 16 times 2 times 524 gives me 16,728. No, 768. 16,768. Divide this by 23. It goes there 729 times. 729 times. So what is the remainder? The remainder is 1. So I've done this, and what I meant is that you don't always need to reduce this, but when you reduce it, it makes your work easier. But if you want, you can maintain it and move with it to the final answer. Now, so I want to show you how to find the inverse now using the Euler theorem. Finding the inverse. This one you look at, finding the remainder. This one you look at the working. You've already done a similar question. So you can just use that example to do this. How do we compute inverses using the Euler theorem? That is the last thing I want to look at today. What does the Euler theorem say? The Euler theorem says that if A is relatively prime to P, then A raised to phi of P will be relatively prime to, or no, will be congruent to 1 mod P. So for me to get the inverse, what I did, I multiplied this equation by the inverse of A. So when you multiply this equation by the inverse of A, the left-hand side becomes A inverse times A phi of P, that is a power. And this other side multiplied by A inverse will be A inverse mod P. So the left-hand side, you can use the law of indices, which says that if I have A raised to 2 multiplied by A raised to 3, the same as A raised to the sum of those two. The sum of those two, which is 5. And it also says that if using the same, if I have A raised to that times A raised to Q, no, phi of P, is the same as A raised to the sum of these two, which is phi of P minus 1. So this is the inverse of A. This is the inverse of A. So that's why I said the inverse of A, therefore, is given by this. So let's find the inverse of 12. The inverse of 12 will be given by 12 raised to phi of 19 minus 1, then mod 19. What is phi of 19? Phi of 19 is a prime number. So 519 is just 18. Then minus 1 mod 19. But what we know is that this will reduce to 12 raised to 17 mod 19. So this is the universe. So we only need now to reduce this. And reducing this, you can use any method. You can use 19 is prime. You can use the Euler, the Fermat theorem, because 19 is prime and it does not reduce, it does not divide it 12. You can use the Fermat theorem to give you the answer. You can use the first powering algorithm that I did here, and so on. Let's use the Euler theorem. Euler theorem says that 12 raised to 5 of 19 would be equivalent to 1 mod 19. So that means 12 raised to 5 of 19 is 18. Is 18. This one is 18 is larger. 18 is larger than 17, so you cannot use the Euler theorem. So that leaves us with the other two methods, or either the Fermat's little theorem or the fast powering algorithm, because 18 is larger than 17. The power that we want is 17. Now, so I use the fast powering algorithms. 12 raised to 1 will be this, 12 raised to 2 will be that, 12 raised to 4, 12 raised to 8, raised to 16, but I want 12 raised to 17, which is 17 is 16 plus 1. So it is 7 raised to 16, which is 7, and then 12 raised to 16, which is 7, then 12 raised to 1, which is 12. This gives us 84. Divided by 19, the remainder is 8. So this 8 therefore becomes the inverse of 12. The inverse of 12. But what is very important is this part. Once you know how to do this part, whatever follows is any of the methods you've learned, you check which one is appropriate for that particular question. Thank you. So that was the last question that I was to do today.
All right, Mwalimu, thanks for that session. So we're looking at some ways where we can get guys to take part in exercises during online sessions, because not everyone has the opportunity to come to the physical labs. So I'd ask guys to kindly have some apps on your phone for drawing, where you guys can like actually write. Just play with that a bit. It might take us a while to adapt to that. Maybe maybe this week. But I think your phones have these apps for drawing. So I was just check if your phone has an app for drawing, where you can use your hand as a pen. Mwalimu has been doing that, and then Mwalimu, I don't know. It might be a bit of a steep hill, because guys might have to connect more than 2 devices. Maybe you have your laptop and then you're also connecting with the phone, which is fine. But I think it would go a long way. Mwalimu, what do you think about that?
Oh, you want a scenario where maybe when we have a class, they can also present in terms of we have questions, discussion, and so on.
Yeah. Maybe like 1 or 2 students or participants can try. Maybe solve a problem.
That is okay. I think it will go a long way to assist most of them, especially where you find that you have a problem and you do it, and then people can assist you to come out of that problem. It will really assist.
Yeah, I know it's
Yeah.
not easy, especially given the platforms we're using. But I know, for example, if you join this call with your phone as well, and then you share your screen, you will be able to try and solve on a problem. So maybe that's something we can look into. Maybe we'll advise in the week or maybe next week. But yeah, I think it would go a long way. Also, some of the participants are probably going through the same issues. So when someone is struggling in class to execute, guys will probably learn really well from others' challenges.
Yeah, that is something we shall, as an office, you will sit and then we think of a way to how it can be done with also the input of the students also, because I know they could be having a way they can advise what can be done. So maybe, as you said, in the course of the week,